So a lot of people come up to me in the street and ask me, Omri, why do we need to adaptively symmetrize the KL divergence? So I hope to answer it here now so they'll finally stop bothering me. So we begin with the general setting of machine learning, where we try to learn some true distribution called pi, but we only have access to finite set of samples or observations. And the common approach to solving it is to define some parameterized distribution, P with parameters theta, and to find the parameters that best minimize some distance to the true distribution. So this distance is some divergence function, and the choice of which divergence we minimize can have a great impact on how we optimize and the quality of results we get. So for example, if we have a true distribution, which is a mixture of two Gaussians, and our model is a single Gaussian, we can we can minimize the KL divergence, which is very easy to compute, but it has a mode covering behavior. So again, it is able to capture both modes, but it also gives some probability to regions that have zero probability. This is partly because of the asymmetry of the KL, because note that if we switch those two distributions, we get what we call the reverse KL, which has the opposite mode-seeking behavior, where it learns only one mode and ignores the other. It also has another problem that is kind of intractable because it requires access to the true distribution. So what we're looking for is a divergence that is both symmetric and tractable. Symmetric is pretty easy because we can just sum up the two KLs to get the Jeffreys divergence. And as you can see, it balances the two behaviors, but it is still intractable because we still have this pesky true distribution value. One way to minimize a symmetric divergence in a tractable way is to use general adversarial networks. This is the general formula, where we use an additional model called psi to evaluate the divergence. So this gives us a symmetric divergence. It gives us tractability, but is it stable? Because we have one objective, which one model is trying to maximize, but one is trying to minimize, and the answer famously is no. So for example, it can cause mode collapse, where even when you use a model that can capture complex distributions, you will still have only one mode rather than a true distribution. This instability can also be seen in the loss function over training, where it just keeps oscillating, but never actually converging. So actually, what we want to minimize is a divergence that is both symmetric, tractable, and stable. And to approach this, we look again at the Jeffreys divergence and try to figure out how can we make this reverse KL term tractable. And we know that GANs add an extra model to evaluate the divergence. So can we just add a model to be a proxy, a surrogate of the true distribution? This allows us to write the Jeffreys divergence in the same way, just replace the true distribution with the proxy, which we can evaluate and basically make it tractable. The only thing we need to make sure is that this proxy is close enough to the true distribution to give us a good approximation. And the way we do that is pretty simple. We just use constraint optimization. So we minimize the forward KL, we minimize the approximated reverse KL, but we also constrain the proxy to be close up to epsilon to the true distribution. But before we start implementing this, we still have some critical decisions we have to make. For example, what should epsilon be? If it's too large, then the approximation is basically meaningless. But if it's too small, maybe it's impossible to solve this problem. And also note that the two KL terms have the same weight, which kind of does make sense because the first one is an exact term, but the second is an approximation. So should we give a bigger weight to the first term, the exact term, which will also cause a bigger focus on the mode covering behavior. So we have all those balances and all those trade-offs. And do you have any idea on how we can solve those balances? Because I have no idea. So we try to reformulate the problem just a little bit using resilient constraint learning. meaning we add 3 more parameters, only 3 epsilons, which we try to minimize, and those are the constraint specifications, meaning they're basically just the upper bounds of the previous KL terms we talked about. And this is what gives us the adaptivity, because during the optimization, the focus will shift from to the most difficult constraint to hold. And once it has the focus, it will become easier and easier, which will make the other constraints more difficult. And then again, the focus will shift to those constraints. And this will give us the adaptivity that will make sure that the proxy is good enough and that both our models, both KL terms are also minimized. But notice that this is still a constrained optimization, which is notoriously very difficult to compute. It requires a lot of heavy computations because we need to make sure every step that all constraints are validated. But luckily, there's another way to solve that, and that is to solve the dual problem, meaning we have some Lagrangian that both our models are trying to minimize. So you see already that they're collaborating rather than being adversarial to each other. And we still have the max min gain, but those Lagrange multipliers, they're actually not really trying to hurt us, they're trying to help us. Imagine the constraints are walls in a room. They're just making sure we're staying inside and not going outside. And this is basically it. This is all we're trying to solve, which is quite simple. And I mean, the Lagrange is pretty simple, no need to go over it. And before we start experimenting, we need to also make some model decisions. I won't go into the reasoning because there's not much time, but essentially for the main model, the p theta, we use normalizing flows. And for the proxy model, we use an energy-based model. So in the first experiment, we want to ask if all the story of duality and resilient learning is actually necessary, and maybe we can just take those the 3KL terms and just use some fixed weight optimization. So we tested that on a synthetic dataset of a mixture of 40 Gaussians. And because we don't really know which weights we should use, we tried 25 different weight configurations, which you can see in the different colors. And our adaptive method is this black line. So we measure the negative log likelihood over the training. And with some weights that they do diverge, but the other weights are still not as accurate, not as good as our adaptive method. So we think this is a pretty good evidence that this adaptivity is actually very beneficial. Next, on the same dataset, we also want to compare with normalizing flows, where we just minimize the KL or maximize the negative log likelihood, and minimize the negative log likelihood. And you can see that the normalizing flow, it starts pretty well, but then starts to diverge. This is because the normalizing flow actually starts to learn the empirical distribution rather than the true distribution, while for our framework, it's not really an issue, it's still stable. We also wanted to see how it behaves if you change the learning rate by comparing with the Wasserstein GAN. So with a small learning rate, which is marked with the x's, you can see that both our framework and GANs converge to some acceptable solution. But once you increase the learning rate by 2 orders of magnitude, the GANs collapse completely, but our small framework is actually able to achieve better results. So we tested this on also different density estimation benchmarks, and in all of them we were able to capture the whole distribution and capture all the modes in a distinct way. We also looked into a conditional distribution formulation and also used some simulation-based inference benchmarks, and we found that it is able to use less simulation in order to achieve better, higher quality results. And I don't think I have much time, so I'll have to conclude here. So our goal was to find tractable and stable optimization of asymmetric divergence. So we used the Jeffreys divergence and approximated the reverse scale with a proxy model. We then used resilient constraint optimization to make the constraints adaptive, and finally solved the dual unconstrained problem. And the results gave us a framework that is more accurate than just KL, more stable than GANs, and doesn't need needs less training samples. So I have a lot of details that I had to skip because there was not enough time, but you can feel free to scan the QR or read the preprint or just ask me directly. So thank you very much for your time.